Hi there. Welcome to today's lecture. Today we're going to be talking about the mole. No, not those little creatures that have whiskers and dig through, many being blind, right? The blind mole rat. No, we're actually going to be talking about a number, and it's very much like a dozen, just way bigger. We're going to talk about how we're going to incorporate that into our study of chemistry, and it is one of the most fundamental components of the field of chemistry. If you think about the basic units of measure, right? We talked about base units. You have things like mass, and you have things like volume, you have things like time, right? Well, the base units, amount is one of those, and mole is the base unit for amount. And so out of the fundamental things that we talk about in chemistry, mole is huge in that. So we're going to talk about that today. All right, so this is 3.3b. And we'll go back to that. So let's look at our objectives here. We want to look at Avogadro's number, which is just another way of talking about the mole. It's a slightly different thing, but basically the same. We want to look at that being the number that represents the number of particles in 1 mole of something. And we want to define and determine the molar mass for an element. Okay, so you should be, at the end of this lecture, able to define the mole in terms of Avogadro's number. Again, sometimes those are kind of interchangeable words, but Avogadro's number is something specific, and the mole is something specific, but we want to parse the difference between the two, but they are similar in concept. I can use the periodic table to determine the molar mass of an element, and I can use dimensional analysis to convert among mass, moles, and atoms of an element. So we're going to do these things. We call it the mole road, and we're going to convert from one thing to another using moles. So let's start out with the mole. And this, again, is the base unit for the amount of the substance, all right? Basically, we talked about the carbon-12 atom and how they use the carbon-12 atom to come up with an AMU, right? The atomic mass unit. Well, they also can talk about carbon-12. And they said, if we had exactly 1 mole of carbon-12, how many particles would that be? Well, the number is 6.022 times 10 to the 23rd. When we talk about Avogadro's number, this is Avogadro's number, okay? However, 1 mole is this many particles of something. A mole is Avogadro's number of something, right? So Avogadro's number is this actual number. Now, Avogadro is the guy that came up with the mole. It's Amadeus Avogadro. And he came up with the mole based upon his study of gases. Okay, so I'm going to talk to you about that here in a second. Why this weird number? Well, it's going to allow us to use atomic masses and molar masses to be equivalent numerically. So when you look at that periodic table and you have the number below all of those symbols, that number can express the number of AMUs, the mass. That's an atomic mass, right? The mass of 1 atom, or the average mass of 1 atom of that element. And if I use that same number, then I can use that number to express the actual mass in grams of a mole of that substance. So for instance, if we were to look at carbon, right, which has 12.01 underneath it, well, the average mass of a single atom of carbon is 12.01 AMU. The mass of 1 mole of carbon is 12.01 grams, okay? All right, so I'm going to pause for a second here, and I'm going to show you some examples. So, here we go. This box right here is a great illustration of what Avogadro came up with, all right? So he basically figured out that at standard temperature and pressure, 1 mole of any gas occupies 22.4 liters. Now, you might be like, 22.4 liters, are you sure, Powers? Because that's like 11 2-liter bottles. You think I could fit 11 2-liter bottles in here? Well, remember, a 2-liter bottle has a lot of open space, right? The curved lines and stuff like that. So yeah, 22.4 liters. So there would be 1 mole of gas particles that would fit in this box at STP, all right? So here's the room, and I'm at STP, and I open it up, capture some gas. That'd be 6.022 times 10 to the 23rd particles of that gas in here. Now, that is a kind of mind-blowing concept to me, because it seems like different gases might have some slightly different sizes, and so they might take up different spaces. But remember, gases are super, super spread out, right? So let's think about what would happen, because I just talked to you about molar mass and why this might be helpful. I said the molar masses. Well, if I had 1 mole of oxygen, it would weigh 32 grams. If you look at the periodic table, you're going to see that oxygen has a mass of 16 grams. And O2, that means 2 of them, right? And so 16 would be the number of AMUs for the average mass of an oxygen atom, but 32, or if you had O2, a molecule, 32 AMU for an O2 molecule, 32 grams for a mole of oxygen, okay? You're like, well, I'm having trouble visualizing a mole, okay? Well, here is a mole of carbon, okay? That's a mole of carbon, 12 grams of it. Let's look at something that is a little bit more familiar to you. I bet you would recognize something that was this color, right? This is what a mole of copper would be. Now, if you looked at the periodic table, you could tell me how much this weighs right now. How many grams does this weigh? Well, look at the periodic table. What do you see? If you look at copper, right there, number 29, you're going to see the number underneath that is 65.39, which means that if I have a mole of copper here, this weighs 65.39 grams. Isn't that cool? Okay, so this one is a mole of aluminum. Now, although it's bigger, it's way lighter. Okay, the aluminum weighs much less than the copper because the aluminum isn't as dense. All right, and so it's bigger, but it's still a mole. A mole. This is going to have less mass. And how much mass is this going to have? Well, look it up on the periodic table, right? Aluminum. What number is this? Number 13. And it says 26.98. That's the number of grams that this would be, okay? Here you've got some iron, and you've got some zinc, that kind of stuff too. All right. So that's a mole of various different substances. You can also do moles of compounds, okay? For instance, here's some sugar, all right? This is sucrose. And this weighs 342.34 grams, okay? It's right about here. Might be a little hard to see that. But that's what a mole of sugar would be, 320 grams. That's a bunch of stuff. It's because it's a compound. It's got a lot of different atoms. It's got carbons and hydrogens and oxygens in that, so it's going to have a little bit more mass, right? All right, so let's continue on. You kind of have a good feeling for what a mole is now, right? And it's kind of funny, I don't know if you noticed that, but the abbreviation for mole, M-O-L-E, is M-O-L. Woohoo, saved a whole E, yay. All right, why do we need the mole? Well, the mole is going to help us to count things, right? Atoms and molecules are too small for us to count one by one, but we can weigh something out and then have a good idea of how much there is, all right? So we can say, hey, we have a mole of this, and that would be a good weight for us. We can only measure amounts of elements and compounds using mass in grams and kilograms, all right? So that helps us. When we do reactions, reactions actually take place on a particle-to-particle, level, but we don't know whether or not one particle is reacting with another, but we can tell you as a reaction proceeds whether or not it's transforming into something else, right? And so we can talk about the reaction between 1 gram of sodium and 1 gram of chlorine, although we might not be able to tell you about a single molecule or single atom of each of those. We can give you good ideas, and it helps us to describe the chemical reactions if we describe things in terms of grams instead of in single atoms sometimes, right? So here's what's actually happening at an atomic level, but what we are going to see is going to be something way bigger than that, right? We're going to see large amounts taking place. Remember that a mole is just like a word, like a dozen, right? Dozen is 12 of something. A mole is 6.022 times 10 to the 23rd of something. It's just another word. We use those words all the time. How many donuts are in a dozen? How many donuts are in a couple, right? How many donuts are in a mole? Oh, 6.022 times 10 to the 23rd, right? Memorize that number. You don't need to know that. We use that all the time. All right, so a mole is the amount of something that contains Avogadro's number of particles, 6.022 times 10 to the 23rd of those particles. And again, allows us to count very small particles through weighing them, all right? So we can say, these are so small I can't count them, yet I can weigh them and tell you about how many there are. It's called the chemist's dozen a lot of times. A mole is called the chemist's dozen. Some interesting facts about a mole. If I had a mole of watermelon seeds, it would be found inside a melon slightly larger than the moon, okay? If I had a mole of donut holes, they would cover the earth and be 5 miles deep, okay? If I had a mole of sand, it would fill the city of Denver 5 miles deep. That's high. And this is high as the tallest, the highest jet planes typically go when they fly. Okay, it's about how high that is. If I had a mole of pennies, that would make 7 stacks that would get all the way to the moon. Okay, and it might be fun if you want to do this for your own. What would a mole of dollars distributed evenly among every person in the world equal? Well, I'll tell you, a mole of pennies would make everybody a trillionaire. All right, so a mole of dollars would make you even richer, right? All right, so mass of 1 mole of a pure substance is called our molar mass. Okay, so we're going to use terms like molar mass. And again, you're going to get the molar mass from the periodic table. The number underneath, which before we talked about as the atomic mass, can now be expressing molar mass as well. We just have to make sure our molar mass is in a different unit than our atomic mass. Our atomic mass is expressed in AMUs, but our molar mass is expressed in grams per mole. Okay, and again, remember that's equivalent numerically to the atomic mass, but it's not exactly the same thing, right? Atomic mass of boron is 10.811 AMU, but the molar mass of boron is 10.811 grams in a mole, right? Grams per mole. But they're found on the periodic table, and if we wanted to talk about how many atoms are in a mole of something, we just use Avogadro's number. 6.022 times 10 to the 23rd of atoms of lithium are in 6.94 grams of lithium, for instance. All right, we're going to skip through that. How do we use the mole? Well, we're going to use it in things called mole conversions. Here's an example of a mole conversion. If I had I needed 3.50 moles of copper for an experiment, how many grams would this be? Right now, we're going to use these moles, and we're going to come up with things like, oh, I need 3.5 moles because of some other types of problems we're doing. And we call them stoichiometry problems a lot of times. We'll learn about stoichiometry a little later. But this is a very common type of problem to say, well, I need a certain number of grams. I actually have to weigh out the number of grams that I have in this, bottle. How many grams is it going to be if I need that many moles? Okay. Some of our liquids, like our acids, they're delivered to us, and some of them are like in 12 molar solutions and 6 molar solutions. So they give us things based upon molarity, and we have to then do conversions for what grams or what volume that is. So our first one that we're going to talk about, this is our first step in the mole road. I like to call it the mole road because you notice that we have kind of like a highway here, right? You've got 2 lanes going in each direction. And so if we wanted to go from mole to mass or from mass to moles, then we could go in either direction, and we would use the conversion factor. So if I wanted to go from moles to mass, I'd have to have moles on the bottom, and I'd have to have grams on top, and that would give me my mass, right? If I wanted to go the other way, if I were given mass and I wanted to figure out how many moles, well, I got to put moles on the top and mass on the bottom, right? Mass has got to cancel out with mass, and so then I'll be left with moles. This is just one of the components of the mole road. The mole road will branch off in a few different places. So let's just keep talking about various parts of the mole road here. All right, so 1 mole equals how many grams? Well, it depends on the substance you're dealing with, right? If I have lithium, it's going to be different than boron. All right, so let's see how that would look. If I had 0.0507 moles of copper, how many grams would that be? Well, let me just throw in my unit conversion factor. I can look at my periodic table, right? If you want to find the molar mass, go to the periodic table. And I say, okay, moles on bottom, so it cancels out with moles on top. And I put grams on top. And then I just do 0.0507 times 63.55 divided by 1 gives me 3.22 grams of copper. Now, we should probably be showing some work in here that shows that, copper, 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 and copper. That's not very good work as far as the element. I want you to have the element in that work as well, okay? But then the moles cancel off and you get your answer. All right, how many moles of chlorine atoms are in 77.1 grams? Why don't you go ahead and pause it? And you're back, all right? Trying to figure that out. You got to start with your given, 77.1 grams of the chlorine. That would be CO. And then I've got to use 1 mole of Cl. Let me go ahead and write those in there because it just kind of irritates me that they're not there right now. Make sure you're doing it right. I don't want you guys seeing bad practice here. 77.1 grams of chlorine. For every 1 mole of chlorine, there's 35.45 grams of chlorine, right? There's a little multiplication sign here. Grams of chlorine cancels out grams of chlorine. Now, the reason that you need to have these elements there is because later on we're going to do problems where you're converting from chlorine and you're going to go to hydrogen or something like that, right? Where you're doing multiple elements. And a grams of hydrogen is not the same as a gram of chlorine. And so that's why we've got to make sure that we have the units can include our element because we're going to be doing more complicated problems after this, right? Later on anyway. All right, so then you can just take that one divided by that one. You're going to get 2.17 moles of what? Chlorine. Don't forget to write that part of your unit. And of course, we can box that as well, right? All right, well, we have moles to particles as another part of our mole road, right? We can use the conversion factor. 1 mole is equal to 6.022 times 10 to the 23rd particles of something, anything. Bicycles, right? Donut holes like we had before, pennies, whatever. But we're going to be talking about atoms. And so if I want to go from moles to particles, I've got to put moles on bottom, particles on top, right? If I want to go from particles to moles, I've got to put particles on bottom and moles on top. Now you're like, what do you mean by particles, Powers? Well, anytime we get something like atoms, ions, molecules, or formula units, any of those kind of things would be particles, okay? So it's just a way to express the types of collections that we have in our chemical reactions, basically, particles. All right, what would we do on a calculator if we were doing this for a calculation problem? Well, let me show you. You can kind of read it here. You're going to use the EE or EXP button. And let me just kind of show you where that is. This is a standard TI-30X2S. That's this button right here, okay? So if you're looking at this button, it has a little EE, and you do second, and then that button, and that's because it's blue. The second, which is blue, makes that one the one that would work. And it kind of looks funny in, appearance when you're doing it. The big thing I want you to remember is I don't want you to use 10 with a little caret on it. Now, some of you might have a button, and this one's okay. You can use the 10 to the x, okay? It'll say times 10 to the x, or it might say times 10 to the n. You can use those buttons. Those are okay, but don't use this button, okay? This button messes kids up. I'm not saying you can't figure out the right answer that way, but don't use that one. Use that button there if you have it, or use the E or EE button, okay, which just means times 10 to the, and then the exponent. Now, when you put it into your calculator, you're going to see a little E like this, all right? So it'll be like 1.07 E24. That E means times 10 to that. It's very important. Notice how I did the value 3 moles, right? And I said 3, and I did 6.02 times 10 to the 23rd, or E to the 23rd. Notice that I didn't do a time sign, and then a 10, and then an up, and then a 23. If I had done that on the calculator, it would be wrong. If I would do times 10 and then do an exponent, it would be wrong. Okay, and I know it seems like it should be, but it's just the way these calculators work. So use that EE button. It won't lead you astray once you learn how to use it, okay? All right, so how many moles of lead contain that many atoms? Let's see if we can practice this, right? We've got to start with what we're given. And so now we're using that part of the mole road that goes from particles to moles. And so we got to think, okay, well, here's our given. What goes on bottom? Atoms is going to go on bottom. How many, right? We've got to do our number of atoms that are in a mole, right? So 6.022 times 10 to the 23rd atoms of lead in 1 mole of lead. And again, we would want you to show the actual work. This is lead, this is lead, this is lead, and then you could come up with an equal sign, right? We want to show that work there. 0.0249 moles of lead, boom, box it, you're done, right? So that would be what you would do. Now I want you guys to try that. Why don't you hit pause it, and now you're back and you're ready to try this one. 2.15 moles. Well, now we're going from moles to particles, right? How many hydrogen atoms are there? Well, let's start with our 2.15 moles of H. Now, again, this time you'll notice that there's an H there. Well, that's good, because there's another way of talking about hydrogen. And this is why it's important to show these units, because hydrogen atoms all by themselves don't even really exist in nature. In nature, they are going to combine with something else. And typically, you're going to find hydrogen in a diatomic state as H2. And if I had hydrogen, if I had said how many hydrogen molecules, that would be H2 and not H, and I'd have a completely different answer, right? So it's important to show these units, but in this case, they just want H, and so I can just say it's 6.022 times 10 to the 23rd atoms per mole, multiply it, and you get 1.29 times 10 to the 24th atoms, times 10 to the 24th atoms. All right, here we go. Now you can do that, right? And again, practice this on your own. There's other types of problems in the book if you want to go to do these. Now we're expanding on our mole road a little bit. Okay, which one have we done so far? Well, we did this one. Okay, this is the part of town we know already. Okay, and this is the part of town we know already. All right, so we've gone to those two places and we followed the road down those two lanes. We haven't followed the road here yet. And here's another part of our mole road. It tells us that we can convert between gas. Okay, that's liters of gas. It doesn't work for liquids. That's liters of gas. Remember we talked about this box? And we can say, hey, there's 22.4 liters of that gas at STP in 1 mole, right? And so now we can go to that next part. Oh, did I just go backwards or forward? All right. Anyway, we're not going to give you an example of that one yet. We will be using that at another point, but right now I just wanted you to see that part of the mole road does exist. All right, so if we're doing mass to particle conversions, now we've got to follow that road in 2 different places. Let's go back to that other one. So now I've got to go from mass to particle, right? So I've got to go from mass, got to go to the moles, and then go to the particles, right? So if this is moles, and this is mass, and this is particle, and this is volume of a gas at STP, then now you can go and you can follow that mole road in a few places. So now I've got to go from here, from this part of town to this part of town, following the mole road, right? And so I've got to use 2 different conversion factors. I've got to use my molar mass, and then I've got to use Avogadro's number. So this is a 2-step process, right? It's a 2-step process, 2-step conversion in order to come up with our answer. Okay, so when we do these, you can set up a grid like this, but again, just to get you ready for McKellips, I would set it up in parentheses, okay? And so 0.020 grams, and again, this is carbon, so good grief, let's show our units, right? And then 12.01 grams of carbon, and again, this is 1 mole of carbon, and let's use parentheses. I'm not going to kill you if you don't use parentheses, but McKellips might. All right, and then we have 1 mole of carbon is equal to Avogadro's number of atoms of carbon, right? And then we can cancel out our grams of carbon. We can cancel out our moles of carbon. We're left with what we're looking for, which was atoms of carbon. So our final answer is 1.0 times 10 to the 21st atoms of carbon. Box that baby up, take it home, and have it for dinner. Okay, all right. Now, let's see if you can do this. Calculate the number of moles in 10 grams of copper. All right, so by deposit, and you're back. How'd you do? We'll see. And again, we can practice these as you come into class and see how you're doing, okay? How many atoms are in 0.3 moles of copper atoms, all right? Pause it, try it, coming back. How many moles of copper are represented by 4.0 times 10 to the 23rd atoms? Pause it, get your answer, come back. Again, those are all ones that you can try, okay? We got lots of practice problems. If you did one of those, you know, come and check with me. I can give you the answers. I'm not going to give you the answers right now. I'll just let you kind of stew in your own worry, right? No. Hopefully, you'll get the good answers, and then you can check with me, and you'll have the right answers. I wouldn't be worried about it. All right. So as a next ticket, this is what you should be able to do after having this part of the lecture done so far. Avogadro's number is the number of particles in 1 mole of any substance, right? What is the molar mass of oxygen? Include units. Okay. Well, are we talking about an oxygen atom or oxygen gas? Oxygen atom would be 16.01 grams per mole. Okay, make sure you check that unit. How many grams are in 3.2 moles of oxygen? Again, are we talking about oxygen gas? Because see, here's the thing. Oxygen does not, like hydrogen, oxygen doesn't exist by itself either. And so if we said oxygen and we were just talking about oxygen like we normally see in nature, it's actually O2. Woo! So if you're figuring that out, that's going to be a different answer than if you figure out O, right? If we were figuring out O, we would be using 16. If we were figuring out O2, we'd be using 32 grams per mole, right? So those things are going to give you different answers. Important to show our units. All right, we're going to skip through that one. All right, so there we go. Thank you. That was wonderful. I hope you had a great time today. I hope you enjoyed this lecture. I think we're done. I feel like I have more to do, but we're already up to the grading, so apparently we're done. So get out there and try it and have fun, and adios. God bless you. Enjoy your day.